Okay, so we're recording. So today we're going to review all the material for test number 2. So that includes capacitors and dielectrics, current, current density, electromotive force, and DC circuits, of course, which includes resistors, resistivity, and things of that nature. So if anybody has any questions, feel free to ask now. And then after I answer some of your guys' questions, we can go through these 3 examples that I have ready and kind of just ask me any questions as we go along. And this time, instead of going through the theoretical stuff first, we'll try to combine the examples with kind of reviewing the theory, so that way we're a little bit more efficient with our time. So does anybody have any questions?
I do have one question.
Okay, go ahead.
So it's about having 2 EMFs within a circuit
Okay.
and doing the Kirchhoff's rules for those. So there's one specific problem I think it's in the quiz.
Mm-hmm.
I think it was like the question 3 or item 3 or something like that.
Okay, do you mean something like this where you have like 2 EMF sources kind of in series?
Yeah. Yeah. No, in parallel.
In parallel. Okay.
Yeah.
So they include resistors then, right?
Yes.
So like this.
Yeah.
Okay, so we have something like this, and then maybe there's something else going on over here on the side.
And then one of the EMFs is like has a higher voltage than the other and all that stuff.
Okay, so go ahead and tell me what quiz item that was again, and I'll pull it up.
It was item 3. It was the one with point A and point B, something like that, and then finding.
Okay, so here's the quiz. And then let me grab the problem. And I always forget that I randomize the items for you guys. So, okay, so here it is. Let me see if I can actually copy the image. Yes, I can. So we'll go ahead and copy the image here. By the way, whenever you have, just before we go in and get into your specific example here, whenever you have EMF sources like this in series, it's okay to add them up. Kirchhoff's voltage law, that's exactly what it tells you to do, right? As I go around a loop, let's say in this direction, I will end up adding those EMF sources together in my Kirchhoff's voltage law equation. Whereas over here in this case, in the parallel case, we might go around a loop like this, right?
Mm-hmm.
And we can see that there's a voltage gain maybe across this voltage source, but then we lose an amount of voltage equal to the current across this resistor times its resistance value. And then we kind of come this way, right? And then depending on the direction of the current on this branch, we may gain or we may lose some potential across this resistor here. And then when we go from high to low across a battery, that's always a drop. So we'd always lose potential. We come back around here and we set that equal to 0. So it's very, there's no rule in general when you have EMF sources in parallel like this with resistors. But in general, if you have EMF sources in series with one another, you can always add them or subtract them if they have opposite polarity. That is always true. But in the parallel case, it's a little bit more complicated. So let me go ahead and clear this. And then I think I already copied that question. Yeah, there it is. So there is the little circuit from the quiz. And what the quiz is asking us for is, let's go ahead and get the parts here. Part A is the current in the upper branch. So I can go ahead and draw that on the paint diagram here. So they want to know the current up here in this branch, and they call that I sub A because we have the point A there in the top branch. And they want to know the current in the middle branch, which maybe we can assume the current is going this way. Maybe call that one let's actually go ahead and follow that notation IB. And then in part C, of course, the lower current then they want to know. Just go ahead and assume it's in this direction again. Of course, no matter what direction I assume that the current is in, I'll just leave this one as I with no subscript. No matter what direction we assume that the current is in, we're going to get an answer that we have to interpret. So, or rather, if we get a negative answer, we would interpret that answer as meaning that we've chosen the current in the direction in which negative charge flows. And so the direction in which positive charge flows would be in the opposite direction. So nothing really goes wrong there. It's just you pick up a minus sign on your current, which maybe you're not used to, but you certainly don't have to go back and do the problem a second time, right? Then finally, the voltage difference between the points A and B here. So VAB means VA minus VB. Okay, so those are the the four things that we're after here in this particular question. And so let's go ahead and start by writing down KVL. Now, you may have noticed going through a lot of these problems that whenever you have a multi-loop circuit like this, you can never solve the question completely by only using KVL. You have to use KCL at least one time. And so what we're going to see here is we're going to have two KVL equations and one KCL equation. Okay. Let's go ahead and start at the point A, and I'll go around the top loop counterclockwise. So I'm going to go from the point A here, and I'm going to go around in this direction like so. Okay, so that's maybe one way I can remind myself where I got this equation from in my notes. So if I go back and look at it, I know what I did. And when we do that here, let's go ahead and try to use some different colors so it looks a little bit less cluttered. We start with 10 volts, again moving counterclockwise against the top loop. We gain 10 volts, and then we gain, because I've selected the direction of the current from left to right, we gain an amount of voltage, which is 2 ohms times that current IA. And then as we come into this middle branch here, we see that we're going to lose potential difference across the internal resistance of that middle battery, minus 1 times IB. And then we're going to lose 5 volts as we cross the terminals of that battery, the idealized EMF source inside the battery. And now we're at the point B here. And so we are going to go across the 4 ohm resistor, so minus 4 times IB. Let me go ahead and draw in that polarity there. So it's plus on this side, minus on this side. Okay, maybe let's try to do it in a way where it doesn't cover up the 4 there. So maybe down here. So, and then as we come up the right side of that loop now, we reach the 3 ohm resistor in the top right, and the polarity of the voltage on that 3 ohm resistor is like this, and so that is a voltage gain of 3 times IA, and this should be equal to 0 because I've returned to the point A. Whenever I return to my starting location, that's when I put equals 0. So we need at least one more KVL equation here. And so let's go ahead and perhaps do the bottom loop. We can do from point B, and we can go around counterclockwise again, like so, starting from the point B. And I'll go ahead and use a slightly different shade of blue here. If we go counterclockwise, then we pick up 5 volts across the idealized EMF source inside that middle battery there. and we'll pick up a voltage gain of 1 times IB, 1 ohm times IB.
Professor, I forgot to mention. I think I think this problem, the 5-volt battery is replaced with 15 in the question.
That's probably your specific question from your quiz. So I'll just cover this. That
Oh,
analysis
okay.
is exactly the same, right? So some of the problems in mastering have a random, right? So not everybody gets the same problem.
Okay.
So we left off adding in a potential gain across the 1 ohm resistor because our current IB is going from left to right. And then we're going to go down to that bottom branch, and the polarity on the bottom branch is like this because the current I crosses again from left to right. So that would be minus 10 times I. And then we will again reach this 4 ohm resistor in the middle, and it will be a voltage gain as we return to the point B. So plus 4 times IB. And then this should be equal to 0 because we've returned to our starting location, point B. KCL, Kirchhoff's current law, is a statement of conservation of charge. Let's go ahead and do it at this point here, that midpoint there of the circuit. We see that the current IB is going in, and the currents IA are going out. Sorry, the currents IA and I are going out. So one way to do it is kind of just write down the 3 currents like this, put equals 0, and then tell yourself, okay, currents going out are going to be negative, IA is negative, and I is negative because those currents are going this way. And then IB is going, IB is also going out, actually. Well, there's a chat, yeah. Didn't this problem, oh, sorry, yeah. Yeah, so people probably just got different answers, so you might have gotten a different one as well. Unless there's a piece of the question that says change it to, which I don't see. Oh, wait a minute. Actually, I think I see what you guys are talking about here in this question. So the 5-volt battery is removed from the circuit and replaced by a 15-volt battery with its negative terminal next to B. Again, though, the analysis would be exactly identical to what we're doing here. So let's just continue on with what we're doing here. Then it just becomes a slightly different problem. So you have that access to another example. So yeah, so it does say replace the 5 volts with a 15 volt, but let's just keep going with what we've got here. Again, it's exactly the same analysis. So you can always go and find wherever you wrote down that 5 volts in your equations here in the analysis we're doing here, and change that 5 volts to a negative 15 volts, and then the analysis would be exactly the same. Okay. The current IB is actually leaving this junction, like so. So IA is leaving, I is leaving, and IB is actually also leaving as we've drawn it here. I got a little bit confused there myself because of how I drew the current IB. I drew it in such a way that it looks like it's heading into the junction, but we need to remember that that current IB is flowing across the battery and that 4 ohm resistor in there. It is not coming in from outside the circuit. So all of the terms here have a minus sign, as I've chosen leaving the point to be negative. But of course, I have a minus on all the terms and I have a 0 on the other side. I can easily just say the sum of all the currents is 0. And that tells you right away that one of the currents here in this problem will end up being negative, right? We can't sum 3 positive values and get 0. Now it's a matter of solving these 3 equations. We have 3 unknowns and we have 3 equations, right? So let's first go ahead and simplify our equations as much as possible. In the top term, I have some numbers I can simplify here. So 10 volts minus 5 volts is 5 volts. I have a 2IA and a 3IA here. So that's going to be 5IA. And I have here, I'll use green, I have a minus 1IB and a minus 4IB. So that's going to be a minus 5IB. And then all of this should be equal to 0. And a nice thing to do here, oftentimes when you're doing these, 3 equations or 4 equations, 3 or 4 unknowns, you want to use matrices to solve these. And the best way to go about doing that would be to write the equation with the constant term on the other side. So 5IA minus 5IB is equal to minus 5. And now this is an equation which we can have as a row in a matrix and then reduce that matrix to solve for all 3 of our unknowns here. The next equation that we have here is kind of, there's nothing really to combine, but I'll move again the 5 volts over to the other side. Let me just go ahead and write the equation in blue here because that's what I wrote first. So we'll go ahead and write it in the following way. And actually I will move this piece over and I will first write plus 0I. Now let's go ahead and write this other one in blue here. So this is going to be 0IA. My mouse seems to be giving me some trouble again. And then IB comes next. So we have 1IB and 4IB is 5IB plus 5IB. And then we have minus 10I. And this will be equal to, again, minus 5. Because I'm subtracting the 5 volts to the other side. Okay, so our last equation, we don't need to change it at all. I'll go ahead and take it and just copy paste it over here. These are our 3 equations that we now use to solve for the 3 unknowns. There are some nice things that I notice about this system here, namely that in 2 of our equations we have a 0, right? For one of our unknowns, that makes things maybe a little bit simpler. We can solve for IA in terms of IB and then plug it into the next equation, right? And things like that. So whatever method you want to use to solve for these 3 currents, is there a particular method that you guys want to see? Do you want to see me do it using matrix methods? Do you want to see me do it using just the standard, solve for one and plug it into another equation? What do you guys want to see? So let me know in the chat, or you can speak up.
Any method works.
Okay, so I would probably, for this particular problem, just actually solve, because it looks like it's fairly straightforward to solve for one of the currents in each of the equations here. Let me go ahead and just scroll over a little bit more actually. So from this equation here, I see that IA is equal to -1 plus IB. And then from this equation here, I see that I is equal to, and notice what I'm doing here. I'm making sure that when I solve, the thing that I put on the right-hand side is the same for both of the other quantities that I'm solving for. Okay, so if I solve for IA, then obviously IB will be on the right-hand side. So I want to solve this second equation so that IB is on the right-hand side. And then I'm going to plug those two into the third equation. And that will give me an answer for IB. So it's a little mistake I see a lot of people making that just kind of gives them a lot of extra work to do right from the beginning. So when you solve these equations, always make sure that you put the same term on the right-hand side. So we're looking to put this term on the right-hand side. Okay, so in order to do that, we'll end up with, by solving for I here, we'll end up with 1/2, because we got to divide -5 by -10. And we'll subtract 5IB to the other side, so it will be negative, but we're going to divide by -10. So it's going to be a plus 1/2 IB. Okay. So now what we do is we plug these two into the third equation. So we have -1 plus IB plus IB, doesn't change. And then I is 1/2. Seems like my mouse is giving me a lot of trouble again. 1/2 IB, 1/2 plus 1/2 IB, and then this should be equal to 0. And now looking at this equation here, we have a lot of stuff we can combine. Let's go ahead and change the color here. So we have a -1 and a plus 1/2. So that's -1/2. We have IB plus IB plus 1/2 IB is 3/2 IB. Lowercase b. And that should be equal to 0. And so if I solve this, what I'm going to end up with is that I have 3IB equals 1, right? So IB is going to be 1/3 of an amp. Maybe we can, I want to solve for this here. So IB is equal to 1/3 of an amp. And our units are indeed amps because in our original circuit, we have ohms for the units for our resistance and volts, right? So our answer will come out in units of amps. Now that we know IB is 1/3 of an amp, then that means that IA will be given by this top equation. So -1 plus 1/3 is -2/3.
Professor,
It's -1.
shouldn't it be 5/2? Because it's 2 IBs, 2 plus 1/2, so that's be 5/2.
Oh, actually, yeah, that's correct.
And then IB would be 1/5.
Right, yeah. Yep, definitely. So it would be 5/2, and then it would be 1/5, right? There we go. And then here, yep, this would also change. So it would be 1/5 here. Maybe I can just, there we go. And so then IA would just be -4/5 then in that case. And then we can also get I from the equation there with IB as well. So I is equal to 1/2 plus 1/2 IB. So it'd be plus 1/2 times a fifth. So 1/2 plus a tenth, right? You gotta multiply top and bottom by 5 on the 1/2. So you're gonna end up with 6/10 here, which we could reduce to 3/5. And now you have your 3 currents. And then where was the other one? Oh, right here in purple. Okay. Now, just to address the specific problem from the quiz, because it does say to replace the 5 volts with a 15-volt battery. When you do that, what should you do here for this problem? You should find every instance. Let me go ahead and use brown here, I guess. Find every instance where you wrote down a 5 volts, like here and here, and that's it. And replace that positive 5 with a negative 15, because it says, oh no, excuse me, no, replace the 5 with a positive 15. It says the negative terminal will be next to the point B. So the negative terminal would be next to this point right here that I'm putting on the circuit. And so it's the same polarity, but it's just an increased voltage. So 5 goes to 15, and then repeat the exact same analysis here that we've just done. And in the quiz, it quotes me the answer here. It says that when you solve for the current in the top branch, you actually end up with 0. So what that means is there is basically the battery has enough voltage to make the potential difference between, and this is maybe, well, let me go ahead and use a color here to kind of illuminate here. So it basically makes the potential difference across these 2 points 0. Okay, so when the potential difference across those, well, actually even further than that, it's even worse than that actually. So it's the potential difference across each of these resistors has to be 0. Otherwise, there's not going to be 0 current. There's going to be current if there's a potential difference across either of these resistors in this branch. So the potential difference across these 2 resistors up here in the top ends up being 0 when you replace this 5 volts here with a 15 volt. Okay, so you should be able to see that when you simplify these equations here. That also means that the current that flows in the circuit in this loop right here is the same current by Kirchhoff's current law. So the current in the top branch and the current in the bottom branch should be the same, since there's 0 current in the top branch. Excuse me, the current in the middle branch and the bottom branch should be the same because there's no current in the top branch. For our particular example though, we had currents in all 3 of the branches, and there is one more part of this quiz question here, and that was the potential across A and B. So let's go ahead and write down Kirchhoff's, well, as a matter of fact, let's go ahead and write down Kirchhoff's voltage law just to be completely cover what we should do here. But let me tell you what I'm going to do. I'm going to use that trick that I used that I showed you guys in class. I'm going to cut straight across from A to B. And then I'm going to go across the 4 ohm. I'm going to go up and go across the 3 ohm. I'm going to do so in this direction here like this. So this orange loop here. Okay, so just make a little box there on that circuit. And so if we do that, so let's go ahead and say the orange box KVL. That's going to be the potential VAB, and then was it, yeah, so current in this direction, so it's a loss of 4 times IB, so VAB minus 4 times IB, and then we're going to actually gain potential as we go across the 3 ohm resistor, so it's going to be plus 3 IA, and that should be equal to 0. Again, we return to our starting location, always put equal to 0. So now if we want to know what VAB is, we just move stuff to the other side. So it's minus 3 IA plus 4 IB. And so we look over here at our kind of our solutions for IA, right? So this one is 4/5 minus 4/5, and then IB is a 1/5. So we can calculate this. So minus 3 times a negative 4/5 is going to be a positive 12/5 of an amp, and then plus 4 times, and then IB, where's IB? Oh, the purple one, 1/5, so plus 4/5. And what we get is, excuse me, these are not amps. These are volts now, because it's 3 ohms times some number of amps, right? So that's a volt. And here it's 4 ohms times some number of amps. So these are volts now. So that comes out to 16/5, right? So if you want to get like an answer here for this, or actually, I guess it's exact. It's exactly 3.2 volts. Right? That completes that example. So were there any questions from that analysis there? The answer that they give when you replace the 5 volt with a 15 volt is 4 volts, not 3.2 volts, if you were wondering about that. So are there any questions regarding that example there? Okay, so we'll go ahead and open the floor again. So does anybody else or same person have another question that they want to go over? And we can address that before we get into the examples that I have ready. Okay, before we get into that, let me make one comment here. I mentioned a matrix method for solving these 3 systems. So how would I do that? What I would do is I would write a 3/4 matrix and use the function reduced row echelon form on that matrix in my calculator. And the matrix would be just the coefficients here. You have to include the minus sign here, so 5, minus 5, 0, and then you put the constant on the other side as the 4th column, so minus 5. Here it would be 0 for the second one, plus 5, and then a negative 10, and then here we have negative 5. And then for Kirchhoff's current law, the coefficients are always 1s or minus 1s. So if you write down a matrix like this, if you can type that into your calculator, I know that if you're using like a TI-89, for example, you can use the brackets like so, and you put the entries with commas, you close a bracket, and then I believe you put another comma and you can open up another bracket, and those brackets represent rows, and then you close the matrix off with another bracket like that, and then there is a function you can access, the reduce row echelon form function, and you let that function act on that matrix, and that will return to you another matrix which has all ones along the diagonal, like so. I have 3 ones like this for the 3 by 3 portion, and then the final portion here will be your answers for your currents. So for example, if we were to actually punch in what we have here, we got IA was, what was the value? Minus 4/5. So we would have a minus 4/5 here, and then IB would be 1/5, and then I would be 3/5. So maybe you want to practice with that. That's a nice way of solving these systems using matrix methods. Of course, you can do it by hand as well. Divide this row by 5 so that you have a 1 in this spot right here. Once you have a 1 in this spot right here, you multiply by some number to cancel, and then you multiply by some number so that when you add this number to this number here, it gives you a 0. Fortunate for us, there's already a 0 here, so you can follow the algorithm now by making this one a 1. Once you make this one a 1, then you can cancel this one out and cancel this one out. And once you've done that, then your last task is to make this number right here a 1. And once you've made that number a 1, then you use it to cancel this one and this one, these two numbers here. And once you've done that, you've achieved reduced row echelon form. And the numbers that you have on the right side of your new matrix where you've done these row operations will be your answers. So I don't know if you guys have seen this in your algebra or calculus or linear algebra courses. So it's definitely something that you want to learn. It makes solving these problems a lot easier. Why did you draw the orange box in that particular area of the circuit? Because I wanted to get the potential VAB. And so I chose the simplest loop that contains VAB that is non-trivial. So that would be the simplest non-trivial loop that has the voltage VAB. If I drew the loop, let's say in yellow here, this loop would have many more terms in the KVL expression. So if I drew the loop like this and I went around this way, this loop would have many more terms. So just from a practical standpoint, I would just draw a smaller loop, right? That has less terms. There's really no other way to get VAB. That's kind of just what you have to do. You have to draw a KVL loop, and then just when you go from the point A to B, you just label that as VAB. Any other questions? Or we can go ahead and get on to the examples that I have prepared. Give me a thumbs up if you're good to go. Lik, are you there? You good? Okay. All right, so we'll go ahead and just get into these examples that I had prepared. I'll go ahead and clean up the side view over here. Go ahead and delete this. So here's an example of a capacitor question. And this question involves a scenario in which the capacitor initially does not have a dielectric, and then at some point a dielectric is inserted between the two plates. And as a matter of fact, this question also includes some analysis of charging up a capacitor and then disconnecting it from the voltage source that charged it. And so there's a lot going on here in this problem. So there's a lot of stuff that we can kind of get out of this problem. So let's go ahead and begin by reading the question, right? So we have a problem, capacitor with and without a dielectric. The parallel plates of a capacitor have an area 2,000 centimeters squared and a distance between the two plates of 1 centimeter. Connected to a potential, the plates are connected to a potential of V equals 3 kilovolts. quite a large potential difference. The capacitor is charged, and then once it's charged, it's disconnected from that voltage source. Okay? So here it's charged, and then it's disconnected. So you have to really pay attention to what's being said in these problems, right? So when a voltage source is disconnected from a capacitor, the charge on the capacitor remains. We insert a dielectric material completely between the two plates, and the potential between the plates decreases to a value V prime is equal to 1 kilovolt, while the charge remains the same. So there, it even reminds you that the charge remains the same here. Oops, charge remains the same. Calculate C, the capacitance of the capacitor. That would be its capacitance when the material between the plates is in vacuum, or is vacuum, I mean. Calculate Q, the amount of charge stored on the capacitor. Again, when there's vacuum between the plates. And then we'll calculate C prime, I've called it, which is the capacitance after the dielectric is inserted between the plates. Then we'll calculate what I call in lecture, I call it kappa. In the book, they use capital K. That's the dielectric constant. And then we'll calculate Qi, what we call the induced charge on the surface of the dielectric. Then finally, we'll calculate the electric field in vacuum when there's no dielectric material between the plates, and then the electric field when there is a dielectric. Okay. So why don't you guys tell me what I should do in order to calculate the capacitance? So let's try to get everyone involved here. So what should we do to calculate the capacitance of this capacitor when we're given this information here? So we're given the area of the plates, we're given the distance between the plates, and we're interested in the capacitance when there's no material between the plates. What should we do? Don't everybody speak up all at once. But surely somebody has an idea here.
I guess I'll go. I was just waiting for other people, but use the equation epsilon naught times the area over the distance.
Exactly.
Yeah.
So this is a simple question. It's just, you know the dimensions of the capacitor, so you calculate its capacitance directly. So if we were to calculate the capacitance here, we have the area in units of centimeters squared, and we have the separation distance in units of centimeters. And so we can leave everything in units of centimeters initially, and we can write 8.85 times 10, and you guys go ahead and calculate along with me here. 8.85 times 10 to the 12 times 10 to the minus 12 farads per meter. These are alternate units for the units of epsilon naught. You can always write epsilon naught as farads per meter. Of course, times the area, which is 2,000 centimeters squared. And then we need to divide that by 1 centimeter. And that will, of course, lead to the cancellation of 1 power of the centimeters here in the numerator. And so what we should do is we should then convert centimeters to meters. So we know that 1 centimeter, or rather we could write it in the following way: 100 centimeters is 1 meter. Like so. And that will give us the correct units for our final answer. So centimeters will now cancel here. And then the meters here will cancel as well, leaving us with units of farads. So you guys put the answer into the chat here. I'll go ahead and calculate the answer myself as well. So put your answers in the chat. So I have an answer here. Okay, it looks like Sean has an answer, Duke has an answer. Yeah, so those answers, oh, it looks like also Henry has an answer here. Oh, Henry, it looks like maybe there was a slight mistake for your answer. Ah, okay, you got it right. That's fine. Like, just try to follow along and get what you can out of it. Maybe watch you can calculate later, like when you're able to calculate. Okay, so that is the answer that I get as well. So let's go ahead and write it down here so that it's in the video. So 1.77 times 10 to the minus 10 farads. And that is, of course, the same as 177 picofarads that some of you have used for your answer. Now, how do we calculate Q? Right? How do we calculate Q? So now we want to do part B here. Is there a particular equation that we should use? Now that we know what the capacitance of the capacitor is,
Q equals T times V.
Q equals C times V, exactly. I'll write it as Q equals C times delta V. Just to remind you, there's always a potential difference, right? It's only differences in potential that are physical. So in this case, it's the simple product of what we've just calculated, the 177 picofarads times the 3 kilovolts, okay? So 1.77 times 10 to the minus 10 farads times 3 kilovolts, 3 times 10 to the third volts. And so, you know, we can probably just do this one in our head, right? 3 times 1.77, right? You're gonna have a 1, a 3, and a 5. And then, you know, do your orders of magnitude as well. Okay, yeah, so Duke and Sean, good. And the units here, you guys have them, but I forgot to write them there. Coulombs. So we can box that one. Maybe use another color here. So there's our answer to part B. Okay, and maybe now we'll go and do C prime now. How do we calculate C prime? Because apparently we can calculate C prime without first knowing what K is, without first knowing what the dielectric constant is. So how can we reason that one out? So we insert a dielectric material completely between the two plates, and the potential difference, or excuse me, and the potential between the plates decreases to a value V prime while the charge remains the same. Anybody have any ideas on that one? C equals Q over V, Sean says. I like it. So let's go ahead and write that out. So C equals Q over V. But let's go ahead and put the primes in here. So we're calculating C prime because now we have a new voltage V prime here. And so the charge stays the same. So it's exactly the same value that we used, or sorry, that we calculated in the previous part. And so I'll go ahead and write it in orange here. So 5.31 times 10 to the minus 7 coulombs. And then we divide that by our new voltage, which was given to us, which is basically 10 to the third volts. So my mouse is kind of giving me trouble here. I'm trying to clean it up here. So what do we get for this case now, for C prime? Well, we're going to get, and I'll put it in green, we're going to get 5.31 times 10 to the negative 10. And that's going to have units of farads. Okay, so now that we know the capacitance with the dielectric, we should be able to calculate what the dielectric is, right? Yeah, Alberto, that's good. Well, first, yeah, so everybody's getting this answer here, so we're clear on this answer?
Yes.
Okay. Yeah, so a lot of these can just reduce to very simple problems. It looks like a daunting problem because there's many parts, but a lot of the calculations are fairly straightforward, and so it's not too bad, right? So now we can get the dielectric constant. Maybe I'll put it in brown here. Okay. And in order to get the dielectric constant, well, we can just recognize that a capacitor with a dielectric would have kappa, or capital K, whatever letter you want to use, times epsilon naught A over D. And this bit right here is simply the old C. And so if we want to get kappa, we take C prime divided by C. Right, we want to increase the capacitance of our capacitors, so we insert dielectric materials between their plates. And so what do we get for this? So we have 177 picofarads. We could convert C prime to picofarads. Could write it as 531 picofarads. And if you do 531 divided by 177, we already did that problem. It's right here. All we did was multiply by 3, right? And so our answer here for kappa is 3. Which is, of course, a number bigger than or equal to 1. So that is a valid value for the dielectric constant. Does everybody understand that part? Give me a thumbs up if we're good here. Okay. Now we need to calculate the induced charge. The induced charge on the dielectric material. Okay. And so let me remind you, and actually I have it over here on the side. I was just gonna switch the share screen over, but actually mastering logged me out. I had the book ready to share. So just give me 1 second here and I'll bring it back up. Just want to share the book now and just remind you guys how we actually calculate the induced charge. But basically you have to remember that when you put a dielectric material inside the plates of a capacitor, you polarize that dielectric material. And so now there are two charge densities involved. There's the charge density of the charge on the parallel plates, and then there's the charge density on the surface of the dielectric material. And so that affects Gauss's law for capacitors with dielectrics. So let me see if I can find it here. Okay, here it is. Let me go ahead and switch the share screen over. And where is the book? Here's the book here. So go ahead and share here. So now you guys should be able to see the textbook. Can you just confirm that you can see it for me? Just give me a thumbs up. Only a couple of you. Okay, so I'm going to assume everybody can see it now. So here's the image of what I was just kind of describing. So when you insert a dielectric material here in between the plates of a parallel plate capacitor, or any capacitor really, what happens is because you've got an electric field there in that space between the two plates, that electric field is going to, exert equal and opposite forces on these little molecules in the dielectric and cause little dipoles to form. And so the charge density on the surface of the dielectric is going to change. It's not going to be zero, which is what it might have been before it was inserted. Now they're going to have a little bit of a buildup of positive charge close to the negative plate of the capacitor, and you're going to have a little bit of negative charge built up close to the positive plate of the capacitor. And ultimately, we know what happens. We know that we can look at an equation that has an epsilon naught in it, and we can replace epsilon naught with epsilon, and epsilon is kappa times epsilon naught, right? So you can go and you can look at all your formulas where you have an epsilon naught in there, and you can figure out what's going on. For example, the electric field is sigma over epsilon naught. So you insert kappa in the denominator, so the electric field is decreased, right? And that makes sense just looking at an image like this, right? The electric field on the inside is going to be less than the electric field would have been in vacuum, because now you have these polarized charges inside this dielectric, which actually oppose the electric field in that region of space. So remember, electric field lines go from positive to negative, and you can see inside the dielectric we have a separation which is opposite the separation on the parallel plate capacitors plates. Okay. And so what we do is we apply Gauss's law and skip the details here, but basically we apply Gauss's law and we find that the electric field now, when we have the dielectric material in place, is going to be given by the surface charge density on the plates minus the surface charge density at the surface of the dielectric, right? So why is that? Well, if you kind of scroll back up here and you look at this image, you can see that when the negative charge builds up close to the positive plate, what that means is like some of those negative charges, when you count them all up, kind of cancel out the positive charges that you count up when you apply Gauss's law. And so there's a lower net amount of charge inside that Gaussian surface because the positives and the negatives add up and cancel, right? And leave you with less overall net charge inside of your surface. Okay. So it's the difference between the surface charges divided by epsilon naught, but we can rearrange this result and find that the induced charge should be equal to the charge density on the plates times this factor 1 minus 1 over k, and this is the induced surface charge density. Now, if you really want to get into the details where to do this, you just go back to the textbook and you write down Gauss's law for a dielectric material, and this stuff just falls right out, okay? But this is basically what we're going to use right here, this equation right here. So the induced surface charge density is the density of charge on the plate times this factor 1 minus 1 over kappa. So let's go ahead now and copy that equation down onto Paint. And here we are. Let's go ahead and maybe use red for part E. So the induced charge Qi is going to be equal to the induced charge density times the area of that surface, that dielectric material's surface, which is going to be the same as the area of the parallel plate, right? And so with this equation, we also recall, this is the equation that I just showed from the book, that the induced charge density on that dielectric is the original charge density times 1 minus 1 over kappa, or capital K here, like this. And we know K already from the previous part. We know K is 3. And so we can calculate this. We go ahead and maybe switch colors here. So this is 3 here. Actually, I used brown for K. So this is going to be 3. Right? And so the induced charge density is going to be 2/3 of the charge density on the plates. So 2/3 times sigma. Right? And of course, to calculate sigma is the total charge on, for example, the positive plate divided by the area of that plate, right? Well, these are things that we know, right? We know what the charge is on the plate. That's in orange. 5.31 times 10 to the minus 7. And then the area is something that was given to us all the way up at the beginning of the problem statement. Let's not forget the factor of 2/3 here either. So that was 2,000 centimeters squared. But we probably should convert that to meters now, since we're gonna, as a matter of fact, we're about to multiply by the same A. So as a matter of fact, we don't really need to do that. So actually, let's go ahead and back up here. Let's go ahead and just leave it as A there. We'll leave it as A. And so the induced charge is going to be equal to 2/3, and then in orange, 5.31 times 10 to the negative 7 coulombs. And then it's A divided by A, right? So this thing divided by A times this A right here. And the two A's cancel. Nice, we didn't even have to worry about the units or even plugging A in. Just canceled out. And then if you remember, this 5.31 divided by 3 is 1.77, and then you multiply that by 2, right? So you're going to get 3.54, right? And that would be our final answer. 3.54 times 10 to the minus 7 coulombs. That's the induced charge there. Now let me make that up better. There we go. Okay, so let me know if I made a mistake there on that. You guys go ahead and calculate that as well. See what you get. Give you guys some time there. So double check that that's the answer. Okay, good. Okay, so that's good enough for me. Next part is to calculate the electric field. Well, how do we calculate the electric field in vacuum, right? We use sigma over epsilon naught. And how do we get the electric field when we have the dielectric? Well, we could do, sigma minus sigma induced over epsilon naught, but really all we need to do is simply replace epsilon naught with kappa times epsilon naught. And so the electric field with the dielectric present will be 1/3 of the value because our dielectric constant is 3. So to get the electric field, let's go ahead and maybe use purple now. We're running out of colors here. So in purple, the electric field is sigma over epsilon naught. Well, sigma, again, is Q over A. And we know what Q is. We have it in orange. So it's going to be 5.31 times 10 to the negative 7 coulombs. We're going to divide that by epsilon naught, which is 8.85. Oh my goodness, my mouse. 8.85 times 10 to the minus 12. And that is going to have units of farads per meter. And we also have to divide by the area because, right, we're doing sigma is charge divided by area. So we need to divide by the area as well. The area is 2,000 square centimeters. It's 100 centimeters for 1 meter. And so if we want to convert this to square meters, it's going to end up being 0.2 square meters. We have to divide this thing by 100 and then divide it by 100 again. So that's the same as dividing it by 10,000, right? So multiply by 0.2 meters squared. And that should give us the answer we're looking for in purple here. Okay, so Duke gives an answer 2.35 times 10 to the minus 17 newtons per coulomb. That's certainly way too small of an answer. So we have 10 to the minus 7 in the numerator, and we have 10 to the minus 12 in the denominator. So 10 to the minus 12 is going to flip up and be a 10 to the positive 12, right? So it's going to be like 12 minus 7, roughly 5 for the power of 10, the order of magnitude, right?
Sorry, I flipped it around. Sorry.
300,000 newtons per coulomb. Okay, does anybody else get a similar answer there for that? Three times 10 to the 5 as well. Okay, good. I think that looks correct. Let me tell you why I think that's correct. Remember how we calculated the capacitance over here? The capacitance right here had this factor of epsilon naught. Well, maybe one way to look at it would be to write it in the following way. You could say that, oops. So 1/2 epsilon naught E squared times the volume should be equal to 1/2 C V squared. And you could probably calculate E from here, and it would actually, a lot of stuff would just be canceling out and would look pretty nice. But yeah, so I believe that is the correct answer. So 3 times 10 to the 5th newtons per coulomb, or volts per meter, same thing. And then for our last part here, let's go ahead and do this purple. We'll do it right here. The dielectric field is going to be the vacuum field divided by kappa. And since kappa is 3, the electric field inside the dielectric is going to be 1 times 10 to the 5th newtons per coulomb. Yeah, Alberto, if you got 3.12, you've probably done the calculation correct, but maybe just some rounding or something in there so that it's not working out exactly. Okay, so any questions about this problem here? That was a long problem, right? Any questions? So for this problem, kind of we were working together. I was doing some work, you guys were doing some work, right? So for this next problem, how about we do it in a way where you guys kind of do most of the work, and then maybe I can help out a little bit if there's questions. Let me go ahead and scroll down and let me introduce the problem. Get rid of this little bit over here in the corner. So here we have a simple DC circuit. And it really is a simple DC circuit because a lot of the elements that we have in here are just measuring devices, right? We just have a voltmeter and we have an ammeter, right, to measure the current and measure the voltage. So use the circuit diagram to determine the following. This is a problem I took from the book, but I modified I added in some extra parts to it. So We have a circuit with a battery. It's got an internal resistance and an idealized EMF source, 12 volts, internal resistance 2 ohms. We connect this thing in series with a 4 ohm resistor, but we also want to measure the current. We want to measure the potential difference across the terminals of this battery. So we connect the volt source in parallel with the battery, and we connect the ammeter in series with the resistor to measure the current. Okay. So the question for you guys to answer now are, what is the reading on the voltmeter and what is the reading on the ammeter? Right. So before I let you guys go to start working on it, why don't you guys give me an idea? What do you do to calculate the reading on the voltmeter? What should you do? So anyone, go ahead and answer. You can put answers in the chat. How do we know, or how can we calculate what the voltmeter will read? So nobody's giving me any kind of input here. Do you guys not understand how the meters work? You have to let me know.
Sorry, wouldn't it read the EMF? Because the voltmeter is parallel to the battery.
The voltmeter is in parallel to the battery. So what does that mean for something to be in parallel with something else? By definition, what can we say about the voltages across those two devices if they're connected in parallel?
That means they're the same.
Right. So if the voltmeter has a potential difference equal to the potential difference across the terminals of the battery, then the voltmeter can only measure the voltage across the terminals of the battery. It cannot measure the EMF, the idealized EMF source inside the battery, at least not in this circuit here. It could measure the potential of the idealized EMF source if only the voltmeter was connected to the battery, but that's not the case here. So Sean put it in the chat that the voltage that's going to be measured by the voltmeter is going to be the EMF minus the drop due to the fact that there's an internal resistance there. Okay. How would we go about now calculating the reading for the ammeter? So somebody besides Duke or Sean help guide us to how we would calculate the current reading. So it's got to be Henry, Alberto, Juan, Sergio, or Leek. How would we go about calculating the reading for the current? So who has some ideas? Okay, we have just absolute silence here. Alberto, Henry, Juan, Sergio, Lick, anybody have any input here? How do we go about finding the value that the ammeter is going to read for the current? Okay, Alberto, Henry coming in to save the day here. So Alberto writes down Ohm's law. Henry writes down Ohm's law. So I think I need to ask you guys to be more specific because you're on the cusp of knowing what to do. So I think you guys have a good idea of what you would do, but it's not completely articulated here in what you've written. So let me try to help you. What do you mean by V? What do you mean by V? There's no V that's labeled here in this circuit. So what do you mean by V? EMF. By EMF, do you specifically mean the 12 volts that's labeled? Okay, what about you, Henry? Do you agree with that? Do you think that V should be the 12 volts? Okay, so now Alberto maybe wants to change his answer, so that's okay. So, or maybe VAB from the previous answer. Let's do the following now. So, let's assume that we can apply Ohm's law here. And V is definitely 12 volts. If that's the case, then what value should I use for R? Because I have something that's labeled R, but if I'm going to use V equals 12 volts, I know I'm going to get the wrong answer if I just do 12 volts divided by 4 ohms. I will definitely get the wrong answer. So what should R be? So Henry says 6. Do you agree with him, Alberto? Okay, good. So yeah, exactly. So do you see why, like, if you just say an equation, you also have to specify kind of like, okay, how are you going to apply that equation, right? So you could know a bunch of different equations, but not know how to apply them. So you got to make sure that you articulate that. So if we're going to use the 12 volts, then we have to use R equals 6 ohms to get the right current. Okay. Alternatively, Alberto, you mentioned using VAB. If we used VAB, then what would we use for R? If we want to apply Ohm's law using the voltage VAB, what would we use for the value of the resistance? 4 ohms, exactly. Because VAB is the voltage across the 4 ohm resistor. Okay, so we can apply Ohm's law here, but we have to be careful that we also keep Kirchhoff's voltage law in the back of our mind here, right? So if we're going to use Ohm's law, we have to use Kirchhoff's voltage law to combine the two resistors into a single resistor. In other words, REQ, right? So really, whenever you write down something like REQ or CEQ, you're technically applying Kirchhoff's voltage law or Kirchhoff's current law, one of those two laws. Okay, so that's good. So now we know how to do parts A and B. For part C, you're just going to do parts A and B again, but you're going to assume that the capital R, that 4 ohm resistor, is a 0 ohm resistor. In other words, you're going to short the battery. When you short the battery, what is the measurement for the voltage? What is the measurement for the current? And, you know, it's obviously a bad idea, right, to short a battery. But if we go through the theoretical process of analyzing that situation when we short the battery, what it tells us is something about perhaps the maximum amount of current that could flow in that circuit, which is a question I've asked later, or it tells you about the maximum amount of power that that battery can output. Okay, so those are some of the later questions there. So once you go through A, B, and C, then I'm asking some questions about power, right? So let me remind you just for these last parts before I let you get started, and I'm sure some of you have kind of already started, those of you who know kind of what's going on. Remember that power for circuit elements is the current that flows across that element times the potential difference across that element. And if you have a scenario where you have a polarity like this, and the current flows this way, then power is dissipated. Power is greater than zero. And if you have a scenario where current flows in this direction, then the power is less than zero. And that is power being supplied to the circuit, okay? In the notes, in the lecture notes that I went over with you guys last time, or maybe 2 lectures ago, I drew these figures here, but in the lecture, I believe I switched the direction of the current, but I kept the potential difference polarity the same. Here, I'm keeping the direction of the current the same, and I'm flipping the polarity of the voltage. The point is the power is greater than zero, and it is dissipating when the current flows from high to low potential. And the power is being supplied when the current flows from low potential to high potential. And whenever power is being supplied, we put a minus sign. Okay, so I think that's explanation enough for you guys to get started working on this example. So what we'll do here is maybe I'll give you guys 5 minutes to work through A, B, and C. So we'll check back in. I'll check back in with you guys in 5 minutes to get here. And then maybe what we can do is check in maybe after like 10 minutes, maybe 5 to 10 minutes. I think probably 10 minutes for this part. So we'll do a check-in in like 5 minutes, and we'll go through A, B, and C. And then I'll give you 10 minutes to work on this next part here. And then we'll check in again in 10 minutes from whenever we start up on it. And then for this part right here, maybe another 5 minutes, something like that. So we're planning here for about 20 minutes worth of time, plus however long I talk about the parts. So maybe let's call it like 30 minutes for this example problem here. But here's what we'll do. So you'll work on A, B, and C for 5 minutes. If you finish early, then just take a short break until we do the check-in. And then I'll go through parts A, B, and C. And then I'll give you 10 minutes. You'll work through D, E, F, G. And if you have some extra time left over, then you can have that as break time. And then when I come and check back in again, I'll go through parts D, E, F, and G. And then I'll give you guys another 5 minutes to finish H and I. And if you have some extra time, again, you can take another break. Okay, so that's the plan. So I will check in with you guys at 8:41. Okay, so go ahead and get started. Remember, you're calculating the voltage measured by the source and the current measured by the ammeter. And then you're doing that again for when big R equals 0. Okay, so I'll meet back with you guys in 5 minutes. Okay, so I'm back. Oh, I see Alberto has put some answers in the chat. 0 to 12 and 12 over 0. Well, that obviously cannot be true, right? We can't have an infinite amount of, of current. Yeah, there's going to be more than 0 current as well, Sean. So let's go ahead and go through parts A, B, and C now. So I'm going to go ahead and clear up some space here. Actually, now that I think about it, I can just kind of scroll over here maybe. Can get rid of some of this. This is work from the previous part. Duke, those answers look very, very reasonable. Those answers look reasonable. Okay, so if we want to know the reading on the voltmeter, then we follow exactly what Sean told us to do, which was that it would be the EMF minus the current times the internal resistance of that battery. We can get this by applying Kirchhoff's voltage law. Just do a loop, which includes the volt source there. But we need to get the current here. We need to get the current. So how do we get the current? Well, the current is part B. The current is going to be 12 volts, exactly as we said. So 12 volts divided by 6 ohms. Why 6 ohms? Well, we have a 2 ohm and a 4 ohm, right, in this bottom loop. So we can do Kirchhoff's voltage law for the bottom loop. 12 volts over 6 ohms gives us 2 amps, right? So if that's the case, then we can plug this 2 amps up into this top equation here, which is 12 volts minus 2 amps times the internal resistance of 2 ohms. And of course, this gives us 8 volts. Okay. So 8 volts is what the voltmeter will read for the voltage across the 2 terminals of the battery. And the ammeter here will read 2 amps. Now, the next part says to repeat parts A and B for R equals 0, shorting the battery. That's this R right here. You cannot make the internal resistance of a battery 0, but you can certainly short the battery and make big R 0. So if we make big R 0, if big R equals 0, oh my goodness, my mouse. If big R equals 0, then I equals 12 volts divided by 2 ohms, not 6 ohms. It's not big R plus little r anymore because big R is 0. It's just divide by little r, which tells us if we short the battery, the current will be 6 amps. And of course, that means that the voltage VAB then, when the current is 6 amps, would be 12 volts minus 6 amps times the 2 ohms. Which would be 0 volts. Okay, and the way you understand that that is the case is because there's no longer a resistor between the points A prime and B prime. So those 2 points A and B, or A prime and B prime, they are connected by a wire with zero resistance. So there's no potential difference between those points. So it makes sense that the voltmeter would read 0 if we short the battery. Okay, so that is parts A, B, and C. So here's part A. Here is part B. And these two parts together make part C. Any questions about those parts there, A, B, and C? If there are no questions, then I'll go ahead and release you for the next part, and I'll give you more time for this part because it's more parts and I think slightly more work. So I'll now give you guys 10 minutes to work on D, E, F, and G, which means that we will pick back up at 8:59 p.m. Okay, meet back here at 8:59 p.m. Go ahead and leave your questions in the chat if you have any. If you calculate an answer, go ahead and put the answer in the chat so others can check their answers. And do this, okay? Don't put your answers for all the parts all at once. If you calculate D, put your answer for D in the chat so that everybody else can be on the same page as you. Or if you're incorrect, then others can let you know, right? Don't give all of your answers all at the same time. So as you complete a part, put that answer in the chat. All right, so I'll see you guys in 10 minutes. Okay, I'm back. So I see a lot of you have the answers here in chat. I would just make note that sources, when power is supplied, power is negative. When power is dissipated by resistors, that is positive. Okay. So Alberto, this is probably wrong, but E192 and F16, yeah, those are significantly off. Let's go ahead and take a look at all four of these parts now, D, E, F, and G. So I'll go through them now for you guys. So D is power supplied by the EMF source. E is power dissipated by the internal resistance of the battery. F is the power dissipated by the resistor R. And verify power balance holds for this circuit. So we're simply using the information that we've already calculated, excuse me, in part A and B to determine all the powers here in the circuit. So the power supplied by the source is going to be minus 12 volts times the current 2 amps. That would be minus 24 watts. So that is the power supplied. So I'll use the script E here, power sub E. The power dissipated by the internal resistance will be positive, and the voltage drop across the 2 ohm resistor is not something that we've calculated explicitly, but what we can do is use the formula I squared times R, which is a formula that combines the definition of power for circuit elements and the fact that Ohm's law also applies for a resistor. So the current here in the circuit is 2 amps. So it'll be 2 amps squared times 2 ohms, or 2 cubed, which is 8 watts. That is positive. The power dissipated by the larger resistor looks the same, I squared times capital R. And the current is the same, it's still the 2 squared, but now it's times 4 instead of 2, so it's twice as much power dissipated, so 16 watts dissipated. And then if we take these 3 and we add them up, then what we end up with is 0 watts, therefore power balance is attained. And so that's parts D, E, F, and G. Are there any questions about those 4 parts? Lick, you've gotten the answers just in time. Okay, so I'll go ahead and let you guys work on the next set of parts here. So the last 2 parts, H and I am not going to give you any hints because I want you to actually think about how you get the answers to these last 2 parts. So that's part of, right? You're prepping for the test. You're going to get asked questions without hints, right? So think about H and I and how to get those answers. Think about it yourself first, and then maybe if you can't figure it out, you can ask somebody in the chat. But for this part, do not put your answers in the chat, okay? But you can answer other people's questions if they ask a question. So we'll meet back here at 9:09 here. We'll just account for a few seconds. Whoops, I typed that in the wrong chat there. So we'll meet back at 9:09. I will see you guys then. And we're back. So, I didn't see anyone put any answers or any questions in the chat, so hopefully that means these two last questions here kind of make sense, but let's find out. So follow along with me and see if you are thinking about this the way that I am thinking about it here. So for question H, what is the maximum possible power output of this battery? Well, the maximum power output for the battery is going to be when the current flow through that battery is a maximum. The battery can supply so much voltage, and power is I times delta V. And so if we can make it so that that battery supplies a very large amount of current, then the battery would supply a large amount of power, right? Okay, so what is the maximum possible current flow then? Well, that's the next question. So now we need to think about how can we figure out the maximum current. Well, since batteries have an internal component of their resistance, that means that in order to attain maximum current flow, we should short the battery. In other words, we should connect the battery to itself with a wire that has zero resistance. And when we do that, we will always be limited by the amount of current that battery can supply because of its internal resistance. But that internal resistance we can't change. We can't make it smaller or make it bigger. Well, actually, we could make it bigger actually by, if it's a battery, we could drain all of the chemical potential energy from the battery and the internal resistance would increase. That's just how we would model that internal resistance. But we cannot decrease the internal resistance of the battery, okay? And so there's always a limit to the maximum amount of current that can flow in a battery, and it's given by this expression here. The EMF source of the battery divided by its internal resistance. This is like saying big R in the circuit that we have here is equal to 0. These are one and the same. So if big R is 0, then the current that's flowing in the circuit is given by E over little r. So what is that value? Well, that's something that we've already calculated. That's 6 amps. That's the maximum current flow for this circuit. And therefore, the maximum power output for this voltage source is 6 amps times 12 volts. Or in other words, 72 watts. But what you would find in practice is that if you were to connect a wire to that battery source, to that battery, then it would never truly supply this maximum amount of the power. So this is really an upper bound that is never actually obtained. If I connected a wire to short the two terminals of the battery, that wire would have a small amount of resistance, maybe half an ohm, maybe a quarter of an ohm, something like that. And so the actual power output of the battery would be significantly lower than this theoretical maximum of 72 watts. That is the answer to H and I. Do we have any questions about that? Let me know. Okay, so it doesn't look like there are any questions. So I'm going to move down to example 3 now. Now, example 3 looks pretty spooky, but it's really not. You just kind of have to trust me on this one. It's not as spooky as it looks. So let's take a look at it here. I've called this problem equivalent circuit. Just had to come up with a problem that had to do with combining resistors, combining capacitors, and maybe a little touch of RC circuits in there to really cover all of the topics for these last three chapters. And so this problem, I think, accomplishes that goal. The only topics we haven't talked about, but of course will be on the test, are the resistance of a wire, a cylindrical wire, the resistance of a cylindrical wire, R equals rho times L over A, that kind of thing. And then also current density. We haven't done a problem here involving current density. And we also haven't done a problem involving the definition of current. So that's maybe another one that will be on the test, but we haven't done here. But in any case, let's go ahead and dive into this one here. So use the circuit diagram to determine the following. Assume the points A and B are not connected to the resistive circuit initially. So assume we don't have the capacitors here at first, okay? So the capacitors are kind of attached on later after question E, or part E of this question. So we can go A, B, C, D, and E first, and then we can now connect the capacitor part to the resistor part, and then ask a couple more questions, and then we'll proceed from there. And if we still have time left, if we still have an ample amount of time to maybe do another problem, then maybe we can think about doing an RC circuit, or think about doing a definition of current type of problem, or a current density type of problem, something like that. So it just depends on what we have left, okay? So here's maybe how we'll do it. Kind of want to do it in the same style as example 2. So let's maybe go through here, and I will give 15 minutes to do parts A through E. You don't necessarily have to do them in order. If you read them, maybe you can do some of them in a different order. And then we'll meet back up and we will go through how to do all of those parts. And actually writing down the equations for this resistor circuit is actually not too bad. This problem looks a little bit more complicated than the first example that we did, or rather not the first example, but the question that Duke had. That quiz question is a little bit more complicated than this resistor circuit. So we can get the currents. For example, there are 4 currents here in this resistive circuit. They actually are fairly easy to calculate. You should see that shortly. You'll calculate REQ. Make sure you verify that the elements that you're combining are indeed connected in series or in parallel. Double check. Remember, when 2 elements are in series, they are sharing the same current. When 2 elements are in parallel, they are sharing the same voltage across their 2 terminals. That's about all I have to say about that. There's an REQ part and there's a CEQ part. So for CEQ, you're calculating CEQ just for that right side portion there, just with the capacitors. So I'll go ahead and let you guys get started on that. So this one will be 15 minutes. I think this one takes a little bit longer. So if you finish a little bit early, you get a little bit more break time. Go ahead and put your answers into the chat. And oh yeah, what is the EMF? Yeah, so I did not list an EMF. So let's go ahead and take the EMF to be, let's go ahead and say the EMF is 12 volts, just like the last part. That's a good catch there. Don't want to do it symbolically. We want to do it with numbers. So that's it. So if there are any questions, throw them in chat, help each other out. Now, if you calculate answers, put them in the chat, okay? So if you finish part A, put your answer in the chat so others can check, okay? So I'll see you guys back in 15 minutes. So that would be at 9:35. Okay, I'm back. How are we doing on this one? Because I noticed that not a lot of people have made it to the answer on part C, or maybe you guys haven't written down your answers yet for part C. Would you guys like me to give some more time, or would you guys like me to just start going over things now? Because what you guys are going to see is actually just applying the rules. We can probably get through A, B, C, D, and E in probably just a couple minutes here. Let me know, do you guys want some more time, or should we just proceed? Who's here? Give me a thumbs up if you're here. Okay, so all right, so so this, you guys are saying more time. So yeah, I think I can give you guys some more time on it. So how's another 10 minutes sound? Do we think that's going to be enough time? 10 more minutes? Remember guys, like these type, like A, B, C, D, E, this would maybe constitute like 5 different questions on the exam, right? So um, we don't want to spend too long on any one particular question for the exam, right? I'm going to make sure that we time manage. Am I on the right track? I1 equals 12 and I2 equals 6. I'm not sure what you mean by, I think I1, is that your answer for part B? What you do is you get the answer for part A, and then you can do E divided by REQ, and then you would get I. So maybe label your currents I2, I3, and I4, so that way I know which resistor they're going through. Do you get what I mean? So which one is I1? I1 through R1. Okay, well that's the same as the answer to part B, right? Whatever you calculate going through the source has to be the same as what's going through R1, right? And then I2, I'm guessing that's the current through R2. So yeah, I think your answer for I1 is incorrect. So first go back and fix up your answer for I1. Let me give you guys 10 more minutes. Feel free to ask questions in the chat. You know, I'm still here. I just turn off the video and the voice, so I can type up some answers for your guys' questions. So Alberto, I'll do that for you here in a second. I'll actually write down an answer for you. Juan, those answers look a little bit more reasonable there. Okay, so we'll do the check-in again. I'll give you guys 10 minutes. So I'll be back here at 9:49, but I'll be here in the chat to kind of to talk with you guys. Okay, we're back again. So I see some of you are kind of getting some of these knocked off now. That's good. So let me just go ahead and start working through it because I'd like to end the session around 10. Maybe we can go a little bit longer if you guys want to, but it's been quite a while, right? So we've done a lot of work here. So hopefully it's been helpful. Let me go ahead and work through these because I think when you see me work through them, then maybe it kind of helps to clue you in how to work through them efficiently, right? So I'll start by getting part A, which is REQ. Okay, well, I start with 3 parallel resistors. Well, to do parallel resistors, it's reciprocal. So 1 over REQ is equal to 1 over 5 plus 1 over 10 plus 1 over 15. And you can go ahead and combine these in some way, maybe a common denominator of 30 here. Sorry for the messiness here, so 11 over 30. And then, of course, we want to make sure that we reciprocate in the end, so that tells us that REQ is equal to 30 over 11. And we can go ahead and approximate this. What is this approximately? I'm sure one of you guys has the answer here. Well, actually, this isn't an answer to question A, so maybe I'll leave it as an exact piece first. So once we get this 30 over 11, that's R2, 3, and 4. We need to add in R1, and R1 is 2. So let me go ahead and add in 2 here. So we want to add in 2 ohms because it's in series. Resistors add in series. So that's the same as 22 over 11, right? So we have 52 over 11 ohms. And this, I think, is what you guys are getting here. So let me go ahead and scroll up and pull the answer. One of you guys can be a calculator here for me. 4.73 ohms approximately. Okay, so there's A. Let me go ahead and move that up here. So let's go ahead and take this piece, delete it. Go ahead and move this piece up over here so that we don't lose it. And my mouse is giving me some trouble here. There we go. We'll go ahead and box it as well here in purple. All right, and now part B here. Recall that part B is asking us what is I through the source. In other words, what is the current through the source? If we have REQ, then we can simply calculate the current as the EMF source divided by the equivalent resistance for the circuit. And so that tells us that the current is 12 divided by, and let's use the exact value here, 52 over 11. And that would be units of ohms. When we do that, we can write down an exact answer here for the current, and that exact answer is 121, or excuse me, 132 over 52, and that is amps. And if we want to approximate that answer, let me grab this sign here. That's roughly 2.7, I think is what you guys were calculating.
2.54.
2.54, okay. 2.54 amps. And that looks about right to me, so go ahead and box that. use yellow. Maybe throw a lightning bolt on it. Haven't seen one of those in a while. Okay, so now that we have the current I through the source, it's actually fairly simple to get the other three currents for a situation like this where we have three resistors in parallel. The way you do that is you use KVL, and I'll go ahead and draw on the circuit diagram here. If we start here and we apply KVL like this, going around in this counterclockwise fashion, and understanding that the potential difference from this point to this point is the same potential difference on all three of these resistors here. So all of these resistors are connected by a wire of zero resistance, and therefore they are sharing that potential there between those 2 points. So let me go ahead and use these letters here, A and B, in my Kirchhoff's voltage law expression. So I'm going to write for part C, I gain a potential difference E, I lose R1 times I, and then I lose VAB. And then I'm back where I started, 0. And that VAB is the voltage across R2, R3, and R4. It's shared by all three of those resistors by definition because those three resistors are sharing the same junction points on the two ends of the resistors. They're connected to the same point, basically. So they share the same potential difference. So that's by the definition of parallel connection. Okay, so what it means is that we have 12 volts here, and we subtract off this current that we calculated, 132 over 52 times R1. R1 is 2 ohms. And that is equal to this potential difference VAB here. Okay, so now we need a calculator. So I've got one ready over here. So 12 minus 132 times 2 divided by 52. And I get for the voltage, I get a, well, it doesn't give me an exact answer here, but let's go ahead and write down this, or can I make it give me a fraction?
Wait, is current 2.54 and not 2?
This is the value I think you gave me, so I'm not sure. Is that the right one?
No, because when you wrote in part C, it says times 2, but when it's B is 2.54.
Oh, the current here is 132 over 52 as an exact answer.
Oh, sorry. Yeah,
Yeah,
never
so
mind.
the 2 is
Yeah, I
coming
mixed
from
up. Yeah.
right there. Okay, so VAB, I'll just write down this decimal answer. So it's minus 5.08 roughly volts. What does that mean that I got a negative VAB? That just means that when I subtracted it off, I should have put a plus sign. So maybe we could change to a plus and then change this answer over here. We could make this one a minus, and then this one would be plus, and that's fine. You don't even have to do that. Just take the magnitude of the voltage. You know which way the current is going, so it doesn't matter that much. And so I have this voltage now, 5.08 volts. It's the same for R2, R3, and R4. So what do you guys think I'm going to do here? I'm going to take I2 is 5.08 volts divided by R2, which is 5 ohms. For I3, I'm going to take 5.08 volts, and I'm just going to divide it by R3, which is 10 ohms. And same thing for I4. I'm just going to take it 5.08 volts divided by 15 ohms, and my mouse just didn't even write anything there. That was interesting. 5.08 divided by 15. So those are your answers there for your currents. And we could get an exact answer here. If we really want to get an exact answer, we could take
Professor, in the chat, they said you forgot to take 12 minus that 5.08 because that's just the product of the R1 times the current. Oh, no, sorry, the current times the resistance 1.
5.08 is 132 times 2 divided by 52. Oh, did I mess it up?
You forgot the 12 minus the EMF. That was in the operation.
Actually, I'm looking at the calculator over here, and I actually did something very strange. Apparently, I didn't erase an epsilon naught that was in there from the previous calculation too, which I don't know how that happened, but yeah, that was weird. Yeah, let me go through that again. Yeah, so 6.92, and it gives an exact of 90 over 13. So yeah, we can go ahead and fix that up real quick. So there was a little mistake there, so let's fix it up. Let's get rid of those, and get rid of those, and clean it up here. So I used brown. So it gives, as an exact answer, it is giving an exact answer this time, 90 over 13. And that is in units of volts. And so probably I should go back now and revert my change here. I did choose the correct sign there. So it should be minus VAB, move the VAB over. Exact answer 90 over 13. Excuse me. Exact answer 90 over 13. Decimal answer 6.92 it looks like. Volts. Oh my goodness. Okay, that's clear enough. So 6.92, so we'll go ahead and fill it in over here too. So 6.92 volts, 6.92 volts, and 6.92 volts. Those are our currents there. For exact answers, we would have, for exact answers here, it's always nice to go for exact answers because then if you want to do like a check later, like Kirchhoff's current law or something, then it's good to have the exact answer so everything cancels exactly. So 90 over 13 is up in the numerator. So 90 over 13 divided by 5, that's going to be 90 over 65. So 1 point something amps for the first one. For the second one, it's going to be 90 over 130. So we're looking at something that's a little bit bigger than half an amp. And then for the last one here, 15 times 13. So 90 over, what's 15 times 13? 195? 195 amps. So yeah, something that's a little bit less than half an amp. So you can go ahead and reduce these a little bit on each of them, it looks like. So go ahead and reduce them. Each of them looks like reduces by at least 5 there. Oh, it looks like Sean to the rescue over here. So 18 over 13 for this one. And this one is 9 over 13. And the last one there is 6 over 13. So it's a lot easier to see if your answers make sense, if you have the exact answers, because then you can apply Kirchhoff's current law and make sure that that holds. If it doesn't hold, then you made a mistake somewhere. All right, so there you go. There's our answers for part C. Now, part D, we kind of already answered part D. We answered part D for R2, R3, and R4. That's that 6.92 volts. And then we kind of also answered it for R1 as well. R1 is simply I times R1, the original I that we got. That's the 132 over 52 times 2. So 264 over 52, or like 132 over 26. 132 over 26, which is approximately what? Something like 5 point something, right? Was it the 5? It was like the 5.08 volts, right? So the voltage across R1, let's call it V1, is this, the 5.08. And then the voltage across 2 is 6.92. But this is the same for all of them. So voltage across 2, 3, and 4, it's all the same. And then finally, part E, we work with this capacitor now. This capacitive circuit, I mean. So what do we do for this thing? Well, we've got all these capacitors here. We got to remember our rules for the capacitors if we want to combine those. Let's go ahead and scroll it down a little so we have a little bit of space here. Now, in order to combine capacitors in parallel, we add them up. So C1 plus C2 is going to be an equivalent capacitor here, like so. So there's a CEQ there, right? And that's C1 plus C2, so that gives 40 millifarads. Then we want to do a CEQ, oh, excuse me, oops, I messed that up. I scrolled down and kind of, I guess I just got a little bit confused myself there. Sorry, C1 and C2 here are in series, not in parallel. And this right here is C3, not C2. So I just kind of misread the circuit there. Let me go ahead and back everything up. So when we have capacitors in series, we're going to replace these two here. We're going to replace these two capacitors with a single capacitor. And so we're replacing it with a single capacitor CEQ. And that CEQ is going to be given, let's go ahead and use our product over sum formula, which is very useful for series capacitors when we have two of them. So C1 times C2 divided by C1 plus C2, like this. And then this thing here is going to be 10 times 30 over 10 plus 30. In other words, 300 over 40, or 30 over 4, or 15 over 2. And that is millifarads. Don't change the units. When you have those capacitors with the same units, your answer will come out to have the same units. So now we have a CEQ, which is in parallel with a C3. So now this capacitor is in parallel with this capacitor here. And so we can add them up. So CEQ, maybe we want to call this like CEQ 1 and 2. So subscript 1, 2 there. And now we'll say CEQ for 1, if my mouse will let me. CEQ 1, 2, and 3 now would be equal to this 15 over 2 millifarads plus C3, because when we have capacitors in parallel, we can just add them up. So plus 4 millifarads there. Common denominator here, we're going to end up with 23 over 2 millifarads. Go ahead and get exact answers if you want to, like 11.5, right? 7.5 for the maroon. 11.5 for the gray here. And then once we combine these two, that's what looks like this right here. So we have a capacitor now, which looks like this. That's CEQ123. Well, now we got to combine that with C4. Maybe I'll do that in blue, actually. Let's change the color now. So we combine those two now. So now we'll go ahead and actually I'm at the bottom of paint now, so I have to make some space. Okay, so now we have CEQ 1, 2, 3, and 4 all combined into one. And those two are in parallel, so it's going to be 23 over 2 millifarads plus the 3 millifarads for C4 there. Again, common denominator, we get 27 over 2 millifarads. Or what is that, 13.5, right? Or excuse me, 13.5. Right. Oh, wait a minute, that doesn't make sense. Did I make a little arithmetic error here? 23 over 2, this is, yeah, this is 11.5. Oh, yeah, I did make an error. So it's not 27 over 2, it's 29 over 2. 23 plus 6, right? 29 over 2. So this is like 14.5. Okay, so that completes parts A, B, C, D, and E. And we have yet to discuss F, G, and H. And since we're past 10 p.m., I will discuss F, G, and H now. But just you can feel free to work on them yourselves if you want to. But I will go ahead and go through them now, and then we'll go ahead and end everything there. So F says to reduce the circuit now that the points A and B are connected. So A and B are now connected. So how do we reduce this circuit? Well, let's go ahead and find some space for us to work here. So I will go ahead and start redrawing the circuit now. I know that R2, R3, and R4 were in parallel before, but are they in parallel still when A and B are connected? The answer is yes, because the points A and B are still shared by those three resistors. So R2, R3, and R4 are still connected in parallel. So I can go ahead and replace those with a single resistor, since I know for sure that those guys are connected in parallel. So I'll call this REQ 2, 3, and 4. We actually already know what that value is too. R1, I'm not sure about R1 yet. Let's not jump the gun on R1. We're not sure if R1 is in series with REQ 2, 3, 4 because the points A and B here now have a little bit more stuff going on. We do know, however, that we can reduce C1, C2. Those are in series. We can reduce those two with C3. They're in parallel. And we can reduce those three with C4, which is... actually, I'm looking at this again, and I connected these three with this one in parallel, and that was a mistake. Is that what I'm seeing a chat message for? Yeah, that is a mistake. Yeah, good catch there. That is a mistake there. It should not be added here. This part is incorrect. Let's go ahead and fix it up here. This part is incorrect right here. This part is incorrect. It should have been 23 over 2 times 3 divided by 29 over 2. Product over sum. Product over sum is the correct combination for series, and C1, 2, and 3 are in series with C4. Okay, so let's go ahead and compute that number now. The 2 in the denominator over here will flip up and multiply and cancel this one. And so what we end up with is 69 divided by 29 millifarads. And so that number is like 2 point, maybe 3, roughly 2.3, something like that. Okay, but we know how to combine them now, so we fixed the error there. So we can now take that value there of the 2.3 millifarads, and we can actually plug that in now, because we know we can reduce the circuit from the point A to B. We can take all those capacitances and combine them, because all of those capacitors lie on the same branch of the circuit, right? So there's no reason why we wouldn't be able to combine those. But it is a little bit complicated now, because R1, there's no clear way to combine R1 with any other element in the circuit. So R1 is kind of a loner now, REQ is kind of a loner, and this capacitance, this CEQ right here, is also kind of a loner now. So there's no way to actually combine any of these. There's no partners that they have there that you can combine them with. REQ and CEQ are in parallel, and together they are in series with R1, but that doesn't mean that R1 is in series with REQ. And it doesn't mean that R1 is in series with CEQ. So this is as far as we can reduce the circuit here. So this answers question F. This is as far as we can reduce the circuit. Now comes question G. Is such a circuit realistic? Well, there is one thing that we discussed in the chapter on capacitors when we were looking at capacitor circuits. And that was that, we can have all these capacitor circuits, but of course, we learned that batteries and sources of voltage always come with these internal resistances, right? And so we kind of understood that, but we didn't analyze that until recently when we discussed RC circuits. So anytime you connect a voltage source to a capacitor, of course, the wires, the internal resistance of the battery and everything has to factor in. And so it's impossible to have an isolated capacitor anywhere in a circuit. The wires must contribute some sort of resistance here. And actually, if you try to analyze this circuit, you will run into a few problems and kind of have to do a little bit of hand waving to make this work, because there's no resistor. There's no resistor here in this branch. So we have to have some sort of resistor. And so that is the answer to question H. If not, what could we do to fix it? We put a resistor here. Put a resistor in series with CEQ. To account.
Can you go over why it's not realistic again?
Yeah, I'll repeat that. So we want to put a resistor in series with CEQ to account for the resistance of the wire. Okay, so it's not realistic simply because wires have resistance. In reality, they have resistance. They're not zero resistance like we kind of model them when we do circuit problems. So if you want to do realistic circuit problems, you have to have a resistor in every branch of your circuit to account for that fact that wires are not zero resistance. So that's just something that we have to do here for this capacitor. The capacitor is made up of a conducting set of parallel plates, for example, if it's a parallel plate capacitor. And those conducting plates, of course, obey Ohm's law. So as the capacitor is charging up, that conductor has a resistance while there's current flowing up onto the plates of the capacitor. They experience resistance. So that's the reason why it's not a realistic circuit there. We would have to add in a resistor. Maybe I'll take some red here and just go ahead and come over here and add in a resistor here. Add in a resistor there with a resistance R. And now our circuit is more realistic. Okay, so are there any questions that you guys would like to address? If not, we can go ahead and end the review session, and I'll get this review posted on YouTube and then email you guys as soon as it's up.
I had a question for the CEQ part, RD. So why is 1 and 2 added like if it was a parallel?
Why is 1 and 2 added? What?
Because for CEQ of 1 and 2,
Yeah, that's
why isn't it
right here?
Why is it not just 30 plus 40 or 30 plus 10?
Capacitors in series do not add. It's the sum of the reciprocals, product over sum.
Okay.
The reason is because the capacitors share the same charge on their plates. They have to share the same charge on each of their plates because of conservation of charge. So I can look at the capacitor, the piece of the two capacitors, in fact, in the middle, which looks like this. So you have these two capacitors like this. I can draw a Gaussian surface, a closed surface through this region here. Well, it's not even really, we're not even applying Gauss's law here. What I'm doing is I'm just drawing a closed surface and I'm asking myself, how much charge is in this material, right? The net charge inside this material has to be zero, right? And so it's impossible because this region here could be vacuum. It's not always vacuum, but it could be vacuum. And so there's no way for charge to flow from this piece to the next piece. There's no way for charge to flow from this piece to this piece. And so the net charge on that middle piece there has to be zero. And so if this capacitor builds up plus Q, I wish my mouse would work here. If this capacitor builds up plus Q, then that means that this plate builds up minus Q, right? Well, if this plate builds up minus Q, then that must mean by conservation of charge that this plate builds up plus Q. And then as a consequence of that, this one must build up a charge minus Q. So by conservation of charge, they must share the same charge. Now, what that means is, of course, they could have different values for the capacitance. So Q equals C1 times delta V1, and Q equals C2 times delta V2. And the net voltage from here to here is delta V1 plus delta V2. So delta V is equal to delta V1 plus delta V2. And this is all in your notes. This is all in your notes, and it's all in some YouTube video that we went over capacitors in. So you may have to revisit that. But the idea here is that V1 plus V2 equals V. And of course, I can replace delta V with Q over CEQ, Q over CEQ, and that has to be equal to then Q over C1 plus Q over C2. Okay, so by conservation of charge, the capacitor plates must store an identical amount of charge when they're connected in series. That's always true. When you connect capacitors in parallel, they now share the same voltage. So they can store different amounts of charge based on their capacitances because they share the same voltage. They do not share the same charge in parallel. And as a consequence, capacitances in parallel add to give CEQ. Okay. So any other questions? If there are no other questions, we can go ahead and end it there. Or if people want to stick around and ask me questions or chat about something, that's fine. But we'll go ahead and end the meeting now officially. I'm going to stop the recording.